So I guess orientation on where we are. So we're in, I think, second of what's probably going to be, I would think, 3 or 4 maybe sessions on streams in our little stream series. So last time we really spent a lot of time talking about this like concept of channels, and so we talked about this Z channel data type, which was something that you could think of as really a generalization of a data flow process in a very general sense here. It was something that required some environment, and it could accept these inputs, and basically had these 3 different input channels of it can accept potentially multiple input elements, and then eventually it gets some kind of either done value or error value that it finishes with, and then it can produce multiple outputs, and eventually it produces some terminal success value or error value. And we spent a bunch of time in our last session kind of working through the intuition for that. And excuse me, because I think I have a sneeze coming on, so that may come in a second. But we kind of worked through that, and we saw how we could actually use this to represent all of these different data types. So when we have this stream that we just think of a stream as it's basically this like source of like, we can just pull more and more of these A values from it, and eventually it's either just going to be done or it's going to fail with an error. Well, that's a channel that doesn't take any inputs, and it emits these elements that are chunks of A values, and then it either finishes with an error or it finishes with just this done signal that doesn't have any information other than saying it's done.
Oh, could we bump
And,
up size just 1 point? There was a request in the chat.
oh, sure. Let's see. Yeah, how is that?
I think that's
Yeah.
probably better, but let me know.
Okay. Yeah. Okay. And then we saw how we could use that to represent some of these other data types here. So we could have a sink that's more a consumer of these values, and it takes in these chunks of inputs, which would basically be the things that are coming out of the stream. And then it can either fail with an error, or it can succeed with some terminal summary value, right? So maybe it's like collected all of the stream values into something. And it also has this ability to emit these like leftovers of if it's like parsing something and maybe it's kind of parsed one object and it got some other stuff that kind of is supposed to go to the next object, it can push that back and say, well, I'm not handling that right now. And that's what it uses this element channel for. And then we can also have this thing called a pipeline that's kind of the middle of a stream data processing pipeline that says, well, I'm going to take in these chunks of inputs and I'm going to output these chunks of outputs. And in this case, this thing can also fail with its own errors. And so these are actually the literal ways that these data types are represented in ZIO here. So I think we had these as like examples, but if I go to like the actual Z stream, and I scroll up here, I can see like I was not making anything up to you. Like this is literally what a Z stream is. It just has this channel inside it, and that's what it is. It's just basically like a case class here.
Oh, we had a question. I think we touched on this
Yeah.
briefly last time, but it's worth, I think, retouching it. Which is,
Yeah.
why Z pipeline and why does Z pipeline and Z sync do not accept an in error?
Yeah. So let's kind of play with that idea first. Oh, I'm sorry. Did you say something? Maybe
No.
Okay, I think there's something off with the audio for a sec. So you could imagine them accepting a in error, but let's think a little bit about like the contract that we want to have here, because a lot of these syncs. So like, let's say that we have my sync, and let's say that this is going to be a sync that's going to fail with like a IO exception, and maybe it's going to take some bytes in, it's not going to emit any output, and it's going to just succeed with the unit value. And maybe let's be a little bit more kind of explicit. This is like a it's like a file writer sync. right? So this is going to like take these bytes that come in, it's going to write it to a file, it's not going to have any leftovers, it's not going to produce any useful value, but it's going to like write all of this stuff to a to some file, and maybe it's going to fail with this IO exception if this file doesn't exist. So what this is saying right now is it's saying that this can fail with an IO exception. So let's say we wanted this error type to not be nothing, to be something else. So one possibility would be, and I think kind of what we were like playing with the other day is like, what if this type was any? You know, we'll call this like ZSync2. Oh, and I think I just need to import. Okay. So let's say that this thing was not this type of ZSync where this is nothing, but it was this ZSync2. And let's think a little bit about what this contract would mean. So this contract here means that I can feed this thing an error of type any. And it says it's either going to give me a success value or it's going to give me an error of type E. And so like in this case, if I've got this, this signature here, this file writer sync, this is saying this sync is going to fail with an error of type IO exception. But what's going to happen here if, let's say I feed into this sync a error that is a string, right? Because I could have string errors, or I could have my domain errors. I could have any error type I want. So if I feed it a string error, and this signature promises that I'm either going to succeed or I'm going to fail with an IO exception, what am I going to do with that? How am I going to satisfy that signature? And so the answer is that I basically can't, right? Of if I don't have a way to, I mean, maybe I can just make up my own IO exception in this specific case, but in general, if I need to produce an error of type E, then I'm taking in an error of type any, and my expectation is that if I feed an error to the sync should also fail with that error. I have no way to honor this signature. So if you kind of go down this road of if you want to accept errors, what you end up doing is you end up basically adding another type parameter. So you could have something of like, maybe we'll call this minus in error, right? And we'll call this plus out error. And then you could have something of this is now not any, but this is in error. And this is out error. And then you've got a little bit of a problem because like this file writer sync, you say, well, what type of errors does it accept? And I mean, maybe we can say that this thing is going to, oops, someone was, I don't know if that was me or someone else.
Sorry, that was me. We
No, we're taking some fancy.
We got some troll question and answer things. Luckily, I think only we can do that.
Oh, okay.
Yeah, that's why we like to have the Discord. I guess I don't want to redirect the troll to the Discord though. Anyway, I mean,
so you can see what we've got here. Like this is kind of a more powerful version of this sync. This is a sync that can both look at the chunks of inputs as well as it can handle errors. So like the actual sync can't handle errors. It just deals with these chunks of inputs. This is our like super sync, or maybe we call it like error handling sync. And this can look at the types of input errors. It can transform them to some other type of output errors. So that's definitely like a valid data type. And one of the cool things about this like idea of these channels is we've got here 3 versions of channels that we think are some of the most useful, that I think these 3 together are going to cover you for most of the things you're going to do. But there may be cases where you say, well, I want something a little bit different. And the fact that all these things are channels under the hood makes it pretty easy for you to do that. So if you decide this error handling sync is something that's really useful to you, you can define this as your own data type, and you can pretty easily define a lot of operators for it just by delegating to the existing operators on channels. But I think you can kind of see, looking at this, that this thing adds another type parameter here. And a lot of times that type parameter isn't very valuable, because like here, if this whole thing has to fail with an IO exception, then what we're really doing here is we're just trying to write the file, then all we're kind of saying is that the error has to itself be an IO exception. Maybe if we wanted to, we could write some fancier syncs that like transform the error type from one thing to another thing. But that's typically just not what people are trying to do with syncs. What you're usually doing with syncs is you're aggregating these chunk of inputs. So what we found is, I mean, there was actually an earlier version of ZIO2 where we had something more like this, and sometimes this had caused type inference issues. It just made the type signatures longer. And what we found, like when we deleted it, we essentially just made things a lot cleaner, and we didn't really get rid of any operators that we were actually using. So no one who was implementing an actual sync was kind of using this functionality that we were providing. But again, because all these things are channels, if you do decide, hey, I like want something like this, or maybe I want some other variant that like only transforms errors, maybe I want like an error pipeline, like you can do all those things, and all those things can be channels.
Cool. Let me just double check.
Yeah, any other? Yeah.
That's good though. So yeah, could I create a Z stream that would direct failed elements to error stream queue hub, kind of like a dead letter queue? It kind of sounds like that maybe what you were touching on. This is certainly possible with lifting the error to either, I guess, as well. Yeah, that might also make sense.
Yeah, I think that does get at one kind of important semantic point, that for all of these things, if you're using this error channel, the contract of a channel is that it can emit 0 or more of these elements, but then at the end, if it's going to finish at all, it's going to fail with exactly one either error or done value. So I have definitely had people kind of have the idea of, well, look, I want to have a stream, but it doesn't just fail with one error at the end. It can fail with one error, and then it can emit another error, and then it can emit a third error. And I think that's exactly right, that's a case where you would want something that was more like a Z stream, let's say, any, nothing, either, my error, my value. The semantics of this is that I can have multiple errors before this stream finishes, whereas the semantics of this is that the stream can emit multiple my values, but eventually, if it has one my error, that will be the last thing it ever does.
Maybe the best to like the next step to clarify some of this would be to actually writing some like getting into the code, right? And
exactly. Yeah. So sorry, I feel like that was like a little bit of a summary, and then maybe became a little bit just like long there. But yeah, hopefully that Q&A was helpful. Yeah. So let's go back. So I think when we were looking at things the other day, we had a little bit of a. We definitely don't want to split our screens here because we're already giant. Okay, so I think we were looking, and I think we were starting with like a relatively simple case of, let's say we've got this map error thing, and we'd like to implement this other operator that, like, let's say we're going to call it map error cause, because we want to be able to transform this error, but we want to do we want to be able to look at the full error. We want to see if there was a die failure. We want to see if there's an interruption, and we want to maybe be able to transform all of those things. So this is a pretty like standard operator that exists on ZIO, but it actually doesn't exist on ZSync, or at least it didn't before I think Adrian added it. But we can kind of do it ourselves here. So this is going to be like this one that maps the errors, but it's just going to map the causes here. And we, at least if we're doing our own operators at the library level. We like to take these traces so that our users get this nice tracing information. I think if you're using ZIO2, you may have kind of seen the nice execution traces, and maybe that's something we can do another session on at some point. And so we might say, okay, well, how are we going to do this? And sometimes we can just do it by using our existing operators on sinks or on streams. So like here, I think we have like a, let's see, do we have like a fold? So we might have like a catch-all cause or like a fold ZIO or something like that. So we might be able to just implement in terms of existing operators. But let's say we don't want to do that, and we kind of need to like drop down to this lower level. And so what we can do, and we'll start with this will be like a relatively simple example, but basically kind of the first insight is whenever we're looking at any of these things, a sink is just a channel, a stream is just a channel, a pipeline is just a channel. And so if we want to make one, we can just access that channel, we can call some operators on it, and we can wrap it back up in a sink. So if I go back here, I could start by doing, okay, I'm going to do this new Z sync, and then I'm going to put something inside of here. And admittedly, I think this one is also given away a little bit by the implementation above. But so we can say, okay, well, we're going to start with our existing channel. And then I'm actually getting autocomplete right now, but let's just go to Z channel for a sec. Oops, that was weird. Why is that not opening for me? Let's try again. Z channel. There we go. And we can see it already has an operator that basically is doing what we want here. And so we could just do map error cause. And there we go. So what we've been trying to do is have as many of these operators implemented at this like channel level so that if you want to add them to sinks, or if you want to implement them in streams, or you have your own data type that's based on channels, it's very easy for you to just kind of call this operator. And this operator, we can make sure in one place we have this logic, and we get it right in that one place. So that's like a relatively like simple example, but I mean, I think that also is like a little bit like, okay, we're just kind of calling the existing operators on channels. So, but still, I think that's kind of a useful thing of like, obviously take advantage of the existing operators where they're there. So, you know, the first thing I would do if I was implementing my own operators, I would see just if it's a stream operator, can I implement it in terms of existing operators on streams? If not, I would go to this channel level and I would say, well, is there just an existing operator on channels that I can use and then I can wrap it back up in a stream? But let's look kind of one level deeper and see how would we implement something that was like really a little bit more from the ground up here to get a little bit of more of a sense of like what this actually looks like. And so maybe let's start with something like just map. Yeah, let's see, let's kind of think about maybe how we would create a pipeline here. So we could say this is going to be in, out, and it's going to take a function from in to out, and it's going to give us one of these pipelines. And this pipeline right now, it's not going to use any environment. It's not going to fail because we just have this pure function, and it's just going to take an input to an output. And you can see we've already got like a real implementation here, but let's see how we might go about implementing this ourselves to get like a little bit more of like kind of an idea of what we can do with some of the low level operators here. And again, like we could just kind of call the map operator, but we're not going to do that because we're going to try to push ourselves to see more about the implementation here. So how could we go about doing this? And so if we want kind of very low level operators with channels, one of the ones that is really useful here is this one called read with. And there's either this read with or read with cause, and it's just like a lot of ZIO operators, just doesn't give you kind of the cause and the error type. But why don't we do read with here? And so let's look at what this signature says. So it basically gives us these, it asks us to give us these three functions. And so, oops. This first one is going to take an in element, which in this case is going to be a chunk of these inputs, and it's going to give us something. Then the second one is going to give us an error, which is going to, in this case, be nothing, because we said these pipelines don't handle errors. And then the third case is going to be the done value. So in this case, because these pipelines work with streams, the done value doesn't have any information. Okay. So let's think about, in this map case, what we would want to do with each of these inputs. So if we read from our upstream and we get a chunk of inputs, what do we conceptually want to do with those inputs?
Call the function on every input.
Yeah. So the very easiest thing to do would basically just be to call like f on the input. There's like a slight one more level of things we do, just because we're doing this like chunking thing. So we don't have an input, we've got a chunk of inputs, but that's no problem. So yeah, so the first thing we could do is we could do in.mapf, and maybe I'll give ourselves just some kind of brackets here so we can do this one step at a time. And maybe I'll call this out. Okay, so now we've got a chunk of these out values. What do we conceptually want to do with these out values then?
Write it to the channel.
Yeah, exactly. And so just like there is like analogy of reading from our upstream, there is an analogy of writing to our downstream. And the operator to do that is actually pretty, I guess, typical. So there's like this Z channel dot write out.
Nice.
So what this says is now we're making a channel, and we can see the compiler is kind of inferring some of the types here. And it's, I think we haven't finished, we've got some question marks here. So it's kind of inferring things not always being the appropriate type. But one thing sometimes I like to do here is, it can be helpful for us to write these out ourselves. So this is a channel that is not going to use any environment. We said it's a channel that doesn't handle errors. All right, let's kind of go up to our little pipeline here. It's going to take chunks of in elements. It's not going to do anything with its inputs. And then it is going to, in this case, it's going to fail with nothing. It's going to have chunks of outputs, and it's going to just return anything. And let's see if we've got, let's see, what have I, let's see, fail. I think I just need to do these last two. Let's just, so this one Maybe I'll come back to this in a second. Just so I can stay compiling. Okay, so this one, I'm going to write my output here. Now, how about if so I'm not supposed to get any error here. So this basically shouldn't happen. But if it does happen, what's something that I could do here to kind of satisfy this type signature so I don't have to have this question mark here?
Well, first, a quick question. So people are asking about Z nothing.
Yeah. Let's look at that for a minute. This is a little bit of a funny thing, and yeah, this is kind of the good thing of the Symposium. We get to, so it's a little bit of a silly thing. Z nothing is basically nothing, because nothing is a type that doesn't exist, and Z nothing is a more specific type that also doesn't exist. So you might ask, why do we have this at all? And the reason we have it is, unfortunately, the Scala compiler sometimes doesn't treat any and nothing in a, what I would say is a fully principled way. And so you may have run into this a couple of times yourself, where like I've had a couple people come to me and say like, hey, I'm getting some warning from the Scala compiler that a type was inferred to be any. And historically, there was some reason for this, because you could imagine a situation where you've got like a list of whatever animals, and you've got a list of strings, and you put them together, and you get like a list of any or any ref or something, and it's probably not what you wanted. So that's kind of what the compilers are trying to warn you about. But you can have a lot of other cases, like you're not using any environment type, and you have a type as any. And yes, the type is inferred as any, but that's exactly what the Scala compiler should be doing. So that's actually something we've kind of tried to work with the Scala compiler team to address with, I think, especially for Scala 2, limited success, but hopefully that will get better in the future. But you have a similar thing with nothing, where the Scala compiler sometimes can be very hesitant to infer nothing as a type, because in some cases, nothing is kind of not what you want to infer, and it indicates maybe you have something going wrong. But as we can see in cases like this, where no, nothing is telling us a very valuable piece of information that this workflow can't fail. Or in our case of pipelines, telling us this very valuable piece of information that this pipeline, this channel doesn't accept any inputs through this channel. So the Z nothing is just basically a slightly different, it's like our version of nothing, that because it's not literally this nothing type, it has better type inference properties with the Scala compiler. So it just makes it a little bit nicer to write code when we do write code with this low-level set of channel operators. And again, most of the time you shouldn't have to do this. If you want to do this map pipeline, you don't have to do it yourself. You can just do zpipeline.map. But if you are working with these low-level implementations, it just makes things nicer where you have to specify fewer type parameters. So that's the background on that.
Cool.
Okay, so a really simple kind of logic here is we could say, well, if we get an error, then we'll just fail with that error. And if we get a done value, then we'll just be done with that done value. Now,
someone did ask if there was a Z any, but it does not appear as though there's a Z.
There's not a Z any. That's actually an interesting thing. Maybe we should look at. I think at least so far we haven't found that that helped us with that, but maybe it would. So maybe that's kind of an area for experimentation here. Okay, so we've got this channel here, and can anyone see something that might be wrong with what we have so far, or kind of a next step that we need to take here? And so maybe one clue would be, so let's say that we got this chunk, we transformed it with our function, we wrote it out. What's going to happen the next time that we read an input.
Are we going to do the same, or we want to do this? We want to do this repeatedly, right?
Yeah, exactly. And
yeah, this kind of reminds me a lot. Maybe you mentioned, but it sort of looks. It's kind of like a ZIO style DSL right now. This is imperative. These are sort of like ZIO effects, except it's a very specific, maybe hyper parametric subset of ZIO.
Yeah, I mean, it is very, like at this level, it's very imperative. Yeah, it's like read this, write that, read this, write that, which in a way, like, yeah, is not the highest level thing, but at this level, we don't necessarily want to be high level. We want to be low level because we want to be able to have a lot of control of exactly what we're doing here.
Yeah,
but yes,
it's doing it once, just to be clear. Right? This is a single read. It's not going to like, this isn't like a constructor that's going to create a channel that will read forever. This is a single read when this effect executes, and then it's going to write once. So yeah, like chain dot forever on this. Obviously, that's probably more complicated than that, but that's kind of like the next step.
Well, that's one thing we can do, or a lot of times a helpful pattern can be that you just want to recurse here. So you say, hey, if you read a value, write that value, and then try to read again, right? See if your upstream has more inputs for you.
I think we got to just make that easy. Or it needs a type. Yes.
Yeah, probably both of those.
So is this accurate now, this type?
Yeah, and let's check, because sometimes, yeah, this can be a little bit, oops.
Oh, okay, what, give me hover, what does it say? This will be fun. Okay, so let's do some mental diffing. I see chunk about versus nothing towards the right-hand side. I think that's kind of the big difference. One is it requires a chunk about, but we give it nothing in that second to last channel.
Mm-hmm. And then we give it any here. Let's see, let me just make sure I got my type signature right here. So we want an in, error, and a done. Oops. So let's maybe copy this here.
Oh, is it because of, oh, or do we have our own Z channel defined?
Oh.
All right.
I feel like we do this.
We've
like
run into that before.
frequently. Yes. Let's
we should come
yeah,
up
maybe
with like X channel, X stream, but for now let's just
object example or something.
Okay.
Yeah.
Yeah. Where did my VS Code go? Uh-oh.
Oops. Yeah, I'm sorry, I'm bouncing this around here. Let me.
There we go. Nice.
Oh, and then let me bring these in here, I think.
Okay, that looks happy.
There we go. Okay, so let me format this. This is a little bit nicer, and then I think we can remove some of our type annotations here. Though I mean, some of these can be kind of nice just to like keep us on the straight and narrow as we're doing this stuff. But let's let this pile. Okay, so now we've got this channel here that says, okay, well let's read from our upstream. We'll transform it. We'll write it, and then we'll read again.
And just to make that, I assume we don't need that now, so that's cool.
Yep, let's, oops, hold on. I think I had some format going as we had to save. So let me just close this for a sec. Let me get that going again. Okay. All right, let me back. Oh, let's see. Back, yeah, okay.
All right, yeah.
So let's get let's get a compilation going again. Okay, great. And yeah, and you see we got rid of these type parameters. That's fine. This I think we are going to need because we're doing this recursive thing here. So if we got rid of this, it's going to say the recursive lazy value needs return type. So we'll leave that. And that's kind of nice documentation for us. And so then this is basically the channel we need. And so I think we can just do new Z pipeline. And let's see. Oh, I think maybe I'm supposed to do it. And let's see. Oops. Oh, okay, hold on. Let's figure out what the right. Okay, so that wasn't. See, I thought I was supposed to do.
Well, what are we exploring at this moment?
We are just exploring. So I want to put this back. Sorry. I just want to put this thing back in a pipeline.
I see.
So I basically just want to do this because the pipeline just has a channel inside of it. But then I am just looking at this, and we may have something that
Oh, it is private.
has too much privacy here. Yeah, because we need a way.
Is there no apply?
Well, that's what I was just looking at.
Or from
And
Scala?
so, oh yeah, I think that's the. See, I'm being.
We don't usually use news, so that seemed like a.
Yeah, no, I just we have. Yep. Let's do that. Pipeline.
From channel. That makes sense.
Yep, very logical.
Okay.
And there we go. So this is like a kind of very low level implementation of this thing, but let's maybe try doing this now.
We had an example with map. We wanted to switch it over to using our map.
Yeah, so I think we can now take this doubler, and I think I can get rid of that Z pipeline here. Okay, and then
and maybe I'll just get rid of this complicated.
Yeah, I know. I feel like we need to go back to like the very simple one of like, yeah, let's
just grab one of these instead of share just random nums.
Yeah, perfect.
Nums, and then we won't even bother with the zipping. Collect 5, and then we could just debug results. There we go.
Okay, so let's try running this. Let's see if we did this correctly. Let's see. Okay, so oh, there we go. Okay, so I guess with the fact that numbers are random, it's slightly hard for us to debug this. At least
do you want to
right
do a
now.
print line? You want to do a print line in our map?
Yeah, well, or what if we just maybe instead of random nums, maybe we can just do to be like very basic. Maybe we just do 1, 2, 3, 4, 5. Then
Sure.
I think we can. All right, so let's look at. So we're going to double these. Then we're going to filter them, and then we're going to collect them up to 5. Okay, so let's see what this does for us. Okay, so we took 1, 2, 3, 4, 5. We doubled it, so we should. Okay, all right, it's going to give us some more, so we can.
Just so that we see that we take 5, but oops, yeah.
I think we're still not going to have quite enough because we are filtering for things that are multiples of 3. So okay, yeah. We've basically got 2, 4, 6, 8.
Let's do even.
Then...
and then make some more. Here, actually, is it going into that line for some reason? Okay, let's just do zstream dot. Is there one that's maybe numbers already, or
you just do the unfold. Yeah,
unfold,
0
right?
and underscore plus 1. Yep.
Is it? Do we need a
I
ZIO?
think you're gonna need. Yeah, you gotta. I think there's also maybe
some. Oh, I see. Some.
Yeah.
So some S and then
S plus 1. Yep. And there you go. And now these aren't. Yeah, these are just like naturals.
Nice.
Okay, so at this point we doubled them, and then we filtered them for being divisible by 2, which all of them were because we just doubled them, and then we took 5 of them. So we're not doing the most exciting mathy things here, but we can see that all of this is working, and this is where we've replaced this actual implementation of this Z pipeline with this one that we did ourselves.
Could we quickly just see like what we have? Just maybe do a quick like, not correct necessarily, but just print out.
Yeah, definitely.
Right. Yes. Okay.
Yeah. You good with that?
Yep.
All right, let's do this.
Cool. Red chunk 1, red chunk 0, red chunk 1, red chunk 2, red. Okay, great. I'm doing print instead of print line. But besides that, let's try that one more time with print line so it's readable. But that looks good to me. And it's not, we're not really taking advantage of the chunkification right now. we're getting singleton chunks just because the default sort of unfold is not going to give us chunks. Though if we wanted
Right.
to, we optimize
Yeah, why
that.
don't we, yeah, well, so one thing we could do here, if we want to show that, let's use this rechunk operator. It's going to rechunk it into chunks of a certain size. And so
Nice.
now let's try running this. And so now you can see we've got these chunks of these larger sizes, and we're transforming each chunk.
Yeah, which
and
is,
so this,
I don't know, I
oh,
just
no, sorry,
find
go ahead.
the sort of the implicit chunking is kind of cool that you could just write rechunk, and none of our other code really needs to know about that. And imagining that our map operator, our doubler, or some other piece of this pipeline would be expensive to do sort of with small chunks. The fact that you could just sort of chain that on there. I know there's so many other, maybe next week we'll get into all the other kinds of ways of doing this, like aggregating within a time frame into chunks and all that. Like it's just kind of a low effort to use, but kind of complicated under the hood.
Yeah, definitely. And so I think the cool thing about this then is like, sorry, let me get back to, okay, our thing here. So like here right now, this is like pretty simple where you're kind of like, I think you'd be a little bit fair in saying, okay, it's kind of cool, it's a recursive function stuff, but like this seems like a lot of effort to just like map the thing, which is totally fair. And I mean, there's obviously this is like an off-the-shelf like operator, so you would need to implement this yourself. But the cool thing about this being so imperative in this way is it's really easy for you to customize this and to do other things that you want to do. So like, let's kind of, let's try to like maybe play with this a little bit, and let's kind of rename this to something that's called map twice. And so what this funky operator is going to do is it's going to read, and then every time it reads, it's going to transform it, but it's going to write the transformed value twice. And so this is actually like really easy to do here of, if I want to write it twice, then I literally just write it twice, right? That's kind of the advantage of having the low level interface. It's like if you're in the while loop and you want to do something, you just do the thing because you can just do whatever you want there. And so let's try now doing this one. Oops. Oh, so I renamed it. So let me, twice.
Cool. 02024. And yeah, well,
Right,
now
so
5, we're because it's chunked, we're taking the final output, so we're getting 02024. So that I mean that makes sense because we're emitting twice as many values, so we don't get to higher values. Yeah.
Right, and I think that kind of gets to also like when you're implementing these, sometimes you do need to be a little bit careful when you're implementing these things of how you implement them, because you want to preserve that chunking invariance property. So like probably if we were kind of trying to clean this up for some reason, maybe this wouldn't be the right way to do it. Maybe we would want to kind of map this thing, and then we would want to like transform this chunk into like one big chunk that had like 0022.
Or
Yeah,
we could concatenate it there. But I mean, I think the output will actually be the same at the end of the world. We're just writing less. So I guess this would be, if that's really what we wanted to do, this might be more efficient because we're not going through the writing. But still, I mean, it kind of makes sense. The output is sort of not viewing the chunks. So we ended up just getting the first five values, the first 5 out values, because this chunkiness gets subsumed into the stream and pipe line.
exactly. And so one of the cool things then is maybe I think that was like a little bit of like maybe a little bit of an arbitrary one of, I'm not sure how often we want to just like map it and then emit it twice, but let's think about another one where like, let's say we want to do some kind of like maybe a scan on it. And so let me see if I can think of like the right signature here. So maybe this is going to take some initial out value and then it's going to take this function that's going to take the out value and the in value into a new out value. And then it's going to emit these things. So before we even kind of get to this implementation, does this like conceptually make sense? This is pretty similar to like the signature of like scan on a collection of basically kind of doing like a fold left, but instead of just emitting the last value, we're going to emit each intermediate value. Does that make sense?
So let's see, out to in to out. Okay, yeah. We're emitting every intermediate. Yeah, I think that makes sense to me. just to make it clear, like if we had that's just a chunk or whatever, or some sort of stream of 0, 1, just to make it really simple. And we called scan on this with 0 and plus like that or something, right? We should expect to see as our output stream of 0, 1, and then 4, and then 8, and then, well, hey, that's helping me, and so on and so forth. So the previous, sort of the rolling sum.
Exactly. And I think there might be some ambiguity of like, should you emit the 0 value first, or should you just emit the first combination? I think maybe we'll do it where we just emit the first combination. But yeah, that's exactly right.
Sure.
So let's think about how we could do this. And so I think this will be a little bit of a cool example because it'll show one more pattern that we can use here, which is, so here we had this pattern of kind of this like recursive function where like we read and then we read again and so on. But one of the things we can do that's really nice here is we can maintain some internal state here. So here, maybe I'll change this to like def read, and obviously I call this kind of whatever I want, but I'll maintain some internal state here. And I think here the state is going to be this out value. And so let's think about what we need to do differently here. So I think, fortunately, the rest of this logic can be pretty similar. I'm going to need to implement this. And then here, I can just read with my initial state. So so I've kind of reduced my problem to needing to implement this.
Yeah, obviously the chunking is going to make it slightly more complicated than if it were a single value, but otherwise it should be pretty straightforward.
Yeah. So let's think about how we could do this. So I think if we've got this chunk of ins, maybe at least for this chunk, we can delegate to the scan operator on collections. So we could say, and I think this will be a fun little, I haven't working an example together. So everyone, please, everyone in the audience too, like check us here. So let's see. So it's not happy with this guy, and let's see why is it not happy.
It needs
in scan.
It needs to be of the same type, I think, or super type. Yeah, there's sort of that awkward constraint here that's not necessary. I think, yeah.
So we may need our own little collection hold on, can't we do
scan left? Right?
Scan left.
Okay. It's sort of like weirdly constrained. I wish those methods didn't exist, but anyway.
Exactly. So I think this is going to give us the first chunk that we want to emit out. I think we may have this issue of like, what does it do with the first element again, and kind of is it consistent with what we want to do? But I think conceptually we're going to want to do z channel dot write that out, and then we're going to want to recurse again. And I think the only kind of question mark we're going to have is what that out value that we're going to do here. And I think it's basically the last value from this thing that we're writing. So I think we could probably do something.
Do we have the guarantee that in is non-empty, or is that, I guess not really, right? Or I guess it depends. I'm not sure.
String operators will try to preserve that guarantee, but I think we should kind of be correct regardless of it. But I think we can do that in a pretty straightforward way. If I think we'd say something like val updated state is equal to like out dot last option dot get or else state.
Yeah. Cool.
Yeah, and so we can get rid of this.
We might need to drop the head from our out or something.
That's kind of, yeah, I think we may have a little bit to look at there, but yeah, let's kind of try this. So yeah, we had this 1, 3, 4, 5. So maybe let me make that our initial stream. So maybe I'll just call this initial. Is C stream 1, 3, 4, 5. And maybe I'll try well, let's initially leave it this way, and then we can kind of look at what it is, and maybe we can play with it chunky. Okay, so then I'm going to change this to be initial. I'm going to get rid of the rechunk right now. And so I'm going to change this to scan. And I think here we'll just make this, 0. And then I think we had just plus, I believe.
It might need to know that that's operating on.
Oh, yes. Yeah, exactly. That's kind of the one thing when you do these like separated. Oh, and then this needs to be like that.
I mean, let's double check, but I'm pretty sure. Or actually,
yeah, no, I think it needed that.
Oh, it did. Okay. I just don't get the errors on my side. Gotcha.
Oops, sorry, screwed you up there. Okay, so let's try running this. Okay, so we got one chunk in that had 1, 3, 4, 5. And then we got back 0, 1, 4, 8, 13.
Yeah, so we do get that. So I think we do.
Yeah, so yeah, we could, yeah. So I think that could be an easy.
And I think that would also be implied, like this happened to be, I think the Z stream that apply operator seems to generate one big chunk, which makes sense. But if there were multiple chunks, we'd probably get multiple intermediate values. Actually, can we just try that real quick before we fix it? Could I do?
Yeah.
Separate this.
I think we could.
I'm going to separate.
Yeah, we could just do rechunk here if we wanted online.
Oh, and that would rechunk into new. Okay, let's do that. That's nice. I didn't notice that would even change existing chunks. Okay, cool. That makes sense. It's called rechunk.
Yeah, and this is another one. If you maybe a fun exercise would be implement rechunk in terms of this pattern that we're talking about here. So yeah, so I think this is So I don't think we like kind of emitting that first value here. So I think that's right. We need to get rid of that.
Yeah.
So yeah, I mean, I think we could maybe do something like out dot.
Or we could just do drop one. I think drop one should work because that's safe. Oh, maybe not.
Let's see.
Oh wait, I'm printing out before what I get, and that's our final result there. That's interesting. Let me drop one.
I think we got a little bit. Yeah.
Let me do drop one. What is that? Is that correct? And let's also print out the current states. Oh wait, I'm in the wrong place. I'm in map. Oh, we're in map. Haha.
Oh, hold on. Did I? Oh, that was silly of me.
Yeah, I kept map for fun. I know you replaced it. I brought it.
No. Yeah, cool. There we go.
All right, good.
So yeah, so we start with 1, 3, 5. We got 1, 4, 8, 13. Great. So I think this is So I think this is a nice example of how we can implement like a little bit less of a trivial operator here, and how having this kind of imperative interface here gives us a lot of flexibility, where when we wanted to go from this like in a way very ordered to like something with the kind of emitting twice that was pretty arbitrary to kind of a different structure here, it was pretty easy for us to go through these because like we just got the ability to say at this like low level, well, read, write, and if we wanted to, we could like read twice and then write, and we can maintain an internal state here. And the other thing that's really nice about this is you can see that all this stuff, we're maintaining state, but we're not using ref, right? We're not using refs or promises or any of those concurrent data types. And within this implementation, everything we're doing is single threaded. So we don't have to worry about concurrency. And that lets these operators be pretty high performance, where essentially all of this is just in the interpreter of these channels. It's just going to run through this stuff. And in cases like this, where we're not doing ZIO workflows, it won't even do ZIO workflows. It'll just do this stuff. So that's really helpful when we're doing things like parsing JSON. We want one of these pipelines to like decode or encode from one format to another. And we want that to be very high performance, because all we need to do is we just need to pull, and transform. And we don't need all the power of like ZIO for like every one of those steps. We just want to do this like pure data transformation of these streams in a very efficient way.
I'm curious, is there a, maybe we can get to this. I think next week we're going to also do some more lower level operators. And I guess we are kind of near the end of time. Yeah, it's actually, yeah, I think next week the plan is just to give everyone a preview, is to sort of do maybe more of a real world use case. So we implemented some of these fundamental operators using Z-channel, but maybe next week we'll just take a look at, okay, well, how can maybe write one that will solve, yeah, like a data transcoding or decoding problem on something, something somewhat real world. If you have any thoughts, it looks like a couple of people actually asked about this. I think, Naveed, you asked, I'm curious to know how I can have some pipeline that can eat bytes and write some decoded data type. Sometimes I might not have enough data, and sometimes I might have too much. Honestly, it seems extremely difficult with having an exact size. So yeah, I think maybe looking at sort of a real world codec.
Yeah, I think that would be a great thing to do. And I mean, I think conceptually, to preview a little bit, like that's where kind of having this like state and having this ability to kind of arbitrarily read and write can come in really handy, because you could imagine, I mean, let's say, you know, we have some way of knowing, do we have quote unquote enough, but we don't know until we like look at what we've got. So you can imagine this state is maybe kind of the like bytes that we have in our buffer. And what we're going to do is we're going to look at the bytes in our buffer. And if there's quote unquote enough, then we're going to write those bytes, the ones that we're supposed to write, and we're going to recurse with whatever leftovers we have. And if we don't have enough bytes, then we're going to read again. And our new state's going to be the old bytes plus the new bytes. And we're just going to do that over and over again. And so it's going to be a little bit similar to this. But yeah, I think that would be a great kind of next version of this that we could work through next time.
That sounds amazing. Yeah, and it looks like, let me just see the other question. Some people did suggest that, just a thought, if there could be some auto adjusting chunk size considering some rule. Some people were asking about, yeah, the chunk size, like the ideal chunk size for big data, or does it depend on the operators? And then some people were, I mean, there was discussion going on saying that it depends on your exact situation, what the ideal size to have for your chunks would be. But that's an interesting idea.
Yeah, there's kind of a default chunk size. I think right now is like 4096, I want to say, but it can depend. It can depend significantly on your data, because if your data is like individual element, then maybe like 4000 is great. But like I've had some people be like, well, you know, each of my elements is itself like a array, and so when you have 4000 of those that are big arrays, then like that gets pretty big itself. So yeah, we kind of try to, I guess, have a reasonable default, but definitely if you're kind of doing lower level things you want to optimize there, those operators like rechunk can be really helpful for you. And we've actually made some changes where like most stream constructors that take in data in like a poll-based format have a parameter now for the chunk size. So if you're reading from some iterator or something, you can specify, here's the chunk size that I want to use. All right, anything else?
I was muted. There was another question. Doesn't the chunk size vary over pipelines? And I think you could have that, right? Like you could have different chunk sizes at different parts. Maybe I'm wrong.
Yeah, so I mean, you kind of think of, first you've got some chunk size that's coming from your upstream, and depending on what your upstream is, that may be always the same, or it may be different, right? You can imagine you have some like maybe your upstream is like pulling from the Twitter API every second. And if there are a lot of tweets about Taylor Swift in the last second, then there are going to be a lot of things in the chunk. And if there's nothing, then maybe the chunk's going to be empty. So yeah, depending on kind of what the upstream is doing, you may get different chunk sizes. And then ideally, what stream operators are going to try to do where possible is preserve the chunks they get. So like in this like map implementation, if we get in a chunk that's X size, we'll try to write out a chunk that's the same size. But there may be some situations where based on the nature of the operator, we can't do that, or maybe we don't want to do that, right? That if we're going to like write this thing twice, maybe we're just going to combine those into one chunk. Could be like an implementation question there. So there may be some operators that may change the size of the chunks, and that could be one case where like that rechunk operator could come in handy, where you say like, okay, I'm done with this step. Maybe it's changed the size of these chunks. Maybe now I want to rechunk them to this new size and have a consistent chunk size for like the next set of things I'm doing in my pipeline.
Sounds great. A couple last questions. Is there a way to know if my stream is running on a blocking execution context or not?
Yes. So there's for both ZStream and ZPipeline, there's like a ZStream from ZIO, and so you could just do something like ZIO.executor.debug, and that would be like a good way to like look at that.
See what executor you're running on.
Yeah.
Then I may have missed one. Oh no, last question, highly requested, been upvoted. Okay, I've asked before whether the chunk can really be empty. Is this not signaled by done? Yes, thank you for reposting that. Yeah, and if anyone's questions I've missed, that's just because I'm switching between screens, and please rebump your questions. But yeah, I think I asked briefly about that, but yeah, maybe it's worth clarifying. Like, can chunk of in be empty? Does that signal doneness? Does that signal something else?
Yeah, so it doesn't signal doneness. It just signals that kind of this read gave you an empty chunk. So like here, I might get an empty chunk, but maybe if I read again, I'm going to get a chunk that has some tweets. So like, let's kind of go back to that like Twitter and like Taylor Swift example. If like I'm pulling the Taylor Swift tweets every 5 seconds, and maybe there's no one's done it and talked about her in the last 5 seconds, then that chunk could be empty. Now you could say, well, maybe it would be nicer if that particular upstream just didn't write anything to you when it didn't have anything. And generally, when we implement stream operators, we'll try to do that. But I don't think that it can be guaranteed that you'll always have something in the chunk there. So you could have an empty chunk right now that's like, hey, I got your request for information. I don't have anything for you right now, but I've acknowledged I've received your request, and I'm giving you what I have right now, which is nothing. You can ask me again in the future, and I may have something for you in the future.
Yeah, I guess I could imagine an operator that might be pretty trivial to write, like that says like don't send non-empty chunks, which would just kind of be like map thing, but it would just check to see if the chunk is empty before writing it. Otherwise, it wouldn't write it.
And otherwise, it would just read again. That would be a very simple operator to implement.
But yeah, it seems like that doneness, as you mentioned, right, is signaled by that third operator that we're handling there.
Correct.
Which I think gets triggered when you call zChannel succeed, right? Anything listening to that would then get past that value in this parameter.
Exactly.
Right? So yeah.
Yep.
Cool. Sweet. Well, I'm seeing a big thumbs up. So I think I think we got through the questions.
Awesome. Yay.
Thanks everyone. I hope this like look into the internet. Maybe one day we could do a Z channel from scratch. It seems kind of increasingly fun actually of an idea. But I know we have lots of other things to cover too. But yeah, next week we'll try to look at something more real world with streaming, hopefully a little more relevant to like everyone who's going to be using streaming, like a real world problem, in case you don't care about the exploration of the innards. But I don't know, I find it pretty fun. So
yeah,
thank you for giving us the grand tour.
Yeah, take care everyone.
Okay, see y'all next week.
Bye-bye.
Bye.